demonstration we call the Lenz's Law demonstration. There's a lot of different demonstrations of Lenz's Law. Sometimes you might just call it magnet through a tube, sort of like clay on a stick, generic name. So you start off with this by showing people a magnet, and you say, notice that this is an aluminum tube and a plexiglass tube. Neither of these tubes are magnetic. And then you say, okay, what I'm going to do is I'm going to drop this through the tube, and you notice that it falls right through, right? Just like this piece of wood falls right through. Then say, all right, so let's try it through the aluminum tube. Notice it took a long time to fall through that tube. So let's just check that out again right now. So I'm dropping this in. 1 banana, 2 banana, 3 banana, 4 banana. It takes 4 seconds to fall through that tube, whereas through the plastic, it takes essentially no time at all. So this is strange. You say, well, wait a minute, this is not magnetic. Why does the magnet fall slowly through the aluminum but not through the plastic? Well, Lenz's law comes into play. What happens here is this is a conductor and this is a very bad conductor. So the aluminum is a very good conductor, and when there is a change in magnetic flux through a material, a voltage is induced. And sometimes, such as in this case, that induced voltage can also cause a current. So here, when you drop this magnet through here, originally there's no magnetic flux, let's say through this portion of the tube right here. So as the magnet is dropping through the tube, initially there's no magnet near here, so there's no magnetic field lines anywhere near this section of this conductor. But then when the magnet gets close, assuming this is a north pole, the magnetic field lines would be going downwards. All of a sudden you've created a magnetic flux through this little ring of this tube, when before there was no magnetic flux. As a result, a voltage is induced in this piece of the aluminum. That causes a current to flow. And it sets it up in such a way, as Lenz's law holds, the induced current opposes the change in flux. So initially, there were downward magnetic field lines. Now there will be upward magnetic field lines created by the piece of aluminum, the current in the piece of aluminum. Now, the short version of this is there's an induced current. That current creates a magnetic field that opposes this magnet. But as you can see, let's say this has a magnetic field down. Well, according to the right-hand rule, the current will be induced such that there's a magnetic field up. It acts exactly like a north pole pushing against a north pole, which slows the magnet down. A tricky point on this, you might be saying, well, what about after the magnet gets through that piece of wire? So, or through this piece of the pipe, I should say. So once it gets through this, now it's below my thumb. Now what's happening is the field lines are going into this pole because it's a south pole. So the field lines still point the same way, but they're getting weaker. That's still a change. And what happens here is there used to be magnetic field lines going downwards, and now as soon as it gets down here, there aren't any. This piece of metal opposes that change. Since it wanted to create downward field lines, it creates a field like this, which is now the north pole facing down. But since this is a south pole, that tends to pull it up. Okay, that's way overkill for most people. So with kids, you just say, there's an induced current. That current acts like a magnet, and that helps impede the motion of the magnet through the metal. Even though aluminum is not a conductor, when the magnet comes through here, you have a changing magnetic field in the presence of this piece of metal. That induces a current, and that causes this opposition force, which impedes the flow. If you want to get crazy about it, you could talk about right-hand rules and directions of field lines. So you would want to assume that one end, say the downward side, is a north pole and the upwards is a south. Magnetic field lines go out of the north and into the south, and the induced current opposes the change. It doesn't oppose the magnetic field. It opposes the change in magnetic flux. And in this case, there is also an induced voltage, but since it's a bad conductor, you don't see much current. So it's not that that same thing isn't happening in the plastic, it's just that the resistance of the plastic is so much, we don't notice this effect at all. Now if we could get a zoom in here, we can take a look at the scale and I'll show you something interesting. So now I'd like to do this in a close-up setting so you can watch something carefully. Notice that right now this is a scale reading the weight of this entire setup. and right now it reads something like 820. So I guess we're reading the mass of this in this case, so 820 grams, something like that. Now what I'm going to do is I'm going to take this magnet and drop it in, and I want you to watch carefully the reading on the scale. So it's going to oscillate around quite a bit, but in general, notice if it goes up or goes down. That's what we're interested in. So here we go. And I think what you could see is, briefly we saw the scale go way down, and then it kind of oscillated a little bit, and then right about as it was to calm down, it jumped back up. And what we're seeing in that case is it jumps up when the magnet falls into the tube. Why? The reason why is this current is producing an upwards force on the magnet. If it hits terminal velocity, we know that upwards force is equal to the weight of the magnet. By Newton's third law, action-reaction, the magnet must exert an equal and opposite force on the aluminum tube, downwards. And that appears in the weight of this apparatus. And we know that that increase in weight, if you do the math and think about it, right, if the aluminum tube holds the magnet up with a force equal to the weight of the magnet, that means the magnet is exerting a force downwards on the tube equal to that weight. So we can get the mass, because the scale is not reading the weight right now, it's giving us grams, that's a mass. So we can get the mass of that magnet, and you can see that I think it was about 30 grams or something. I'm going to do this one more time, and you can check this really carefully. So here we go. Changes by about 30 grams. It comes out of the tube, it goes back up. Now there's not a lot of friction in here, that's why we see it oscillating for a long time. And that's the Lenz's Law demo.